Okay, I think we should get started. Thanks, everyone, and welcome to this week's SMART webinar. It's a pleasure to have Joseph Paffenholz and Michael Oristaglio, who work on the SEAM project here with us today. Together, they have decades of experience in geosciences, energy geosciences, and geophysics and remote sensing. And they're going to talk today about the SEAM, which is a SEG collaborative research program, about some of the history and some new upcoming opportunities with that. I think you'll find that it's very relevant to the things we're trying to do here within SMART. So without further ado, thank you, Joseph.
Okay, thank you very much. Thank you for the opportunity to talk about SEAM here. So this gives a very broad overview what SEAM is, how it's organized, what we have done in the past, and what we think what might be good ways to do in the future. So my partners in crime here are Mike Oristaglio. He's one of the project managers. He's from Yale University. And Bill Abriel, he is a former SEG president. And so what is SEAM? So SEAM stands for SEG Advanced Modeling Corporation. It is a non-for-profit corporation which is wholly owned by SEG. So what SEAM does is organizes collaborations between oil companies and also geophysical contractors to work on projects which will be too large, too expensive to work for any one of them. So the collaborative is really kind of operative word here. So this is one of two operative words, the way I see SEAM, which defines and maybe sets it apart from some other ventures. It has been established in 2007, so it's now 13 years old. And the prior example of something like this has been the SMART, also SMART, but 2A, a joint venture, a private operative, and it was Chevron, ExxonMobil, BP, BHP, Texaco. So many don't exist anymore, but still, it 4 years, and it had was quite successful, because what came out of it is benchmark model data sets which are still being used. 3D surface multiple attenuation, which was developed by Delft University, but they only had a 2D program, and the 3D and theory people knew how to do it, but to give the push to do the development which was necessary in terms of computational investment, that was done with all the muscle behind it, who went to the contractors and said, okay, we give you money and try it out and see what it does. And since then, of course, it's a standard procedure in marine processing. Another very important game changer, really, is multi-azimuth acquisition, because SEAM discovered, due to modeling, we'll hear more about that, what you really needed to solve some of the subsalt imaging problem is you need multi-azimuth. So 3D SRME and multi-azimuth was a big result from the SMART joint venture. And the SMART joint venture bears a kind of bit of same genetics as the SEAM. It's no surprise, really, because both were conceived by Bill Abriel. So once he conceived SMART, and then once he saw the success, he said, why don't we do this on an SEG-wide basis? And,
hey, Joseph, this is yes. Bill Abriel. I'm only going to make one comment, which is hello and thank you.
Okay, very good. So how are we organized? So it is a tight coordination between SEAM and SEG. So SEG knows exactly what we are up to, what we are doing. But we are fiscally independent of SEG. So we don't take any money from SEG. We pay the SEG for some services, administrative services. So we have about 1 FTE staff So that's the Director of Operations, Shelley Oakley, and she does the day-to-day interfacing with the project and what has to be done, talking with contractors, finances, and so on. And we have accounting that needs to be done, of course, professionally. IRS needs to sign off on it, and that's done also by accounting professionals at the SCG. The governing body of the team is the Board of Directors, which is pro bono. There are currently 9. And here you see the names of the current. So we tried to get a good mix from industry, academia, and also government labs. So the most important thing of the Board of Directors is the financial oversight, so that not money is spent than we have available, and that the money is spent on things we really ought to spend it on, and not on things we shouldn't spend it on. And also sets policy on matters like data storage and distribution, data licensing contracts and the pricing for the licensing, and also working on new project development. So the way that works in the past is companies choose to join individual projects, and I'll talk about which projects we have done in a minute. And typical rates are 60K a year for 3 years. So that's an example from the current Life of Field project. In return, they get the results for the project, and they retain exclusive rights to this for 2 years following completion of the project. After the 2 years, SEAM takes ownership of the results of the models of the data, and then licenses the data to anybody who wants them. There are different pricing schemes for commercial companies and academia. Then the participants, to varying degrees, they participate directly into the program as a volunteer effort. They take a certain task, like building models or doing working on designing exactly the experiments and the computation and so on. Otherwise, third parties which are contracted to open bidding carry out major model building and simulation tasks. And this is where most of the money is spent. The project manager, like Mike Starklio, are under contract to SEAM and manages each project. And the BOD, as I said before, approves the contracts and provides the final financial oversight. So, okay, why would you want to do something like this? What are the benefits for SEAM? For once, we have to get non-proprietary benchmark data to develop algorithms and workflows and compare results to the known ground truths. And known ground truths is, for me, kind of the second operative work which defines SEAM. So far we have done, we have complicated models. The state of the art in terms of refinement and realism. And yeah, you can really test what your algorithms are good. But how you do that if you don't know the answer? And whether by engineering and so on, if you don't know the answer, you can go back in circles for a long time. So having an on-the-ground truth, I think this is a big advantage of SEAM. It does not mean that we wouldn't consider any research or process which doesn't have synthetic data. Right now we have one AI, which with some of the participants don't want to deal with synthetic data. But still, for me, that's an important component. Because you know the ground truth, you can do quantify uncertainties, difficult projects in geophysics always, and you can test acquisition designs spatially and frequency. Frequency, I mean, for 4D projects, how often do you have to do this to see changes? You get training data for interpretation, and overall you have a learning tool for interdisciplinary collaboration. Reservoir engineers in geophysics, as long as I am in the industry, it's always, okay, we need to get those guys talking to each other, they speak different languages. This might be a tool where they can go together and collaborate, whether they know the answer and see whether they come up with the right workflow. It's not going to happen about a $1 billion white-knuckle project in the field. It hasn't happened so far. Okay, here are the projects we have done so far. I go through them later on, a little bit more detail. And you see the companies which have participated. I'm not completely sure that's all on there. You see REPC here. REPC, of course, it doesn't really exist anymore, but it has been a very good collaboration with REPC in the past. So we are very grateful for that. Okay, what kind of data do we acquire numerically? Surface seismic data, so they're all viscoelastic, anisotropic, and we get full azimuth geometry. And then you can later on, you can take out whatever you want to test, the things you want to test. Also, gravity, magnetic and electromagnetic data, and the whole full suite of borehole data and DAS data. Electromagnetic and all the logs you might want. Okay, here's the first of what we call phase 1, which is from 2007 to 2013. It was 25 participants and REPC. And at first, so it was designed to be able to work on subsalt imaging issues. You see the complicated salt model, Gulf of Mexico. At the beginning, it was only acoustic, because at that time, 2007, a model like this could not be calculated. The data could not be calculated with elastic. Later on, later in the project, 5 years later, also did some elastic simulation. This just shows that SEAM tries to be at the leading edge of what can be done with current technology. The phase 2 really was all land data and 3 models. So the Barrett unconventional model has geologic features found in unconventional and introduced orthorhombic anisotropy. And right now people are looking at this model scratching their heads, because the results are not what is expected in terms of what can you find out with where you have so much near-surface noise. And Mike later on might talk also a little bit about this. So this just to see that it was really state-of-the-art. Some people think, oh, synthetic data, they are just shooting fish in the barrel. They don't have any relationship to real data. Solving problems with synthetic data doesn't mean anything. To those people, I would say you haven't seen SEAM data, because if you do it this complicated, this refined, you get some surprises. The ERIC model, we have a shallow and buried cast, a lot of surface multiple scattering, and then finally we have the foothills model, rough topography, like in the foothills of mountains in this case, South America. The next project for 2015-2017 was the pore pressure prediction, and that was 11 participants plus REPC. And that is, the purpose was to get a benchmark seismic data set that can be used to test pore pressure prediction methodologies. Again, you know the answer, and you know whether you do the right thing or not. And what was done here is, what we haven't done before is add basin modeling to the phase 1 model. So you see it's the same phase 1 model, the same salt here. Do basin modeling and then come out with rock physics and come up with pore pressures. And then you see pore pressures, go to rock physics, and then you arrive at the seismic parameters so you can do the numerical simulation. So it's actually the other way around. What you usually do, you look for seismic velocities and try to find out what about the pore pressures. And then REPSI gave some money for the what was technically the pore pressure extension, but then now we call it the time-lapse pilot, and that added the 4D component to the modeling. So it's the turbidite reservoir. The overburden is fairly simple here, but then it requires a whole suite of new issues. So it's a linkage now between geology, reservoir simulation, to the geomechanics and geophysics, and we can now look at changes in gas saturations and oil water pressures and so on. So the whole thing, what we later on did much more refined and more complicated in life of field, and Mike will talk about this. But when the first results came up, that was quite exciting because to the best of our knowledge, it was the first time that in numerical simulations we could see gas coming out of solution as a function of depletion of the reservoir and compaction of the reservoir and, by orders of 10 centimeters, I think it was per year. So before we didn't know, okay, can't we really simulate the 4C process in the computer? So, and that gave us the confidence to start with the Life of Field project. I'm not going to talk more about it. Mike will do that in more detail, who is the project manager for this project. Just the idea here is have a geologic model so you can look at what you need to do to manage a reservoir. And so it is really a field management simulation to calibrate the sensitivity of time-lapse service responses to reservoir changes. So how much changes do you have to have so you can see it in 4D seismic? Just a slide, I'm not going to talk about it really. This is the current project just started up. This is the SCG Artificial Intelligence Project. And Mike also will talk about this a little bit more detail. He is also the punishment for this one. So, and with this, I hand over to Mike, who will do the second. After Mike is finished, I will come back and talk about the future, what we have in mind, what we might do in the future for him. Thank you. So I stop sharing.
Terry, let me ask, how long, I know this runs for 1 hour and 20 minutes. Usually like the talks, I would assume to finish in 1 hour. Can everyone hear me?
Yeah, I can.
I can hear you. We're scheduled for 1 hour.
Oh, you're scheduled for 1 hour. Okay. So I'll try to go quickly. Does everyone see my screen, see models and data?
Yes, I see it.
Yep.
Okay. All right. So I'll talk briefly, as Joseph mentioned, about the two SEAM projects that are currently in progress, SEAM Life of Field and SEAM AI. But as Joseph mentioned, I wanted to show a couple of examples from the models and data that are now available to the public, the projects that are already completed. And I'll go quickly through those to highlight some of the things that Joseph described. This is just showing the list again that Joseph put up. Just to point out, there's been a natural evolution in the technical goals of the projects. Phase 1, mainly concerned with modeling and imaging. Phase 2, with quantitative characterization of the subsurface. And then, as Joseph mentioned, pore pressure and SEAM Life of Field are looking at predictive modeling. And then last, SEAM AI will be looking at whether some of the most time-consuming geophysical data processing steps can be automated with machine learning. Just to emphasize what Joseph said, if you haven't seen seam synthetic data before, it's easy to mistake for real data. This is just an example of a shot gather. It's a collection of recordings when the shot is at the position that's shown in the arrow on the slide in the seam phase model, and you have hydrophones in the water with the source collecting the pressure at different distances. You look at the data panel on the right, and even an expert geophysicist would have a hard time distinguishing that from field data. Really, the key is that when the source is turned off, there's no background noise, but it's easy enough to add background noise to these synthetic data and make it even look more like real data. This is just showing when the shot actually gets close to the salt body, which you see in red here, then the reflections from the interfaces, the layers, and the salt get all jumbled together, and you get this very complicated collection of data traces that you see on the right. Just to point out that everyone shows this model. Joseph did this display as illustrating what the seam phase 1 model looks like. It's actually an image of the model. So this is not a display of the model. This is a display of the seismic image. And it illustrates that when you actually know the seismic velocities, the speed at which the seismic waves travel in the earth everywhere, which of course you do know when you construct the model, then you can form more or less a perfect image. But of course, the real challenge is you don't know what the seismic velocity is in the earth, and you can only sample it at very isolated locations with well logs. So the velocities have to be extracted from the data themselves. That's called now full waveform seismic inversion. It's a more complicated process than just imaging. And this slide shows an example of a challenge that SEAM has put out into the public domain, illustrating the perfectly clear image that you get on the left side of this slide if you use the actual seismic velocities in the model to image the data. You see the layers abutting up against the salt perfectly well. But then as you go to the right of the slide, the velocity field was degraded, typical of the errors that you would get in processing seismic data to recover the velocities. And as you can see on the right side, which should more or less be a mirror image of the left side, the quality of the image has pretty much disappeared. And this is actually a public domain challenge where both human interpreters and if someone wanted to try a machine learning or an AI application on this, they were challenged to actually extrapolate the correct interpretation of salt, across the salt, and that's available that challenge is available on the SCG website. I won't say much about pore pressure prediction. Joseph talked about it, and there's ample documentation about this project in the reports that were submitted to RIPSI and NETL. Just to come back to what Joseph mentioned about the unconventional model, the Barrett model. The goal for this model was to test the state-of-the-art in seismic processing to characterize complex anisotropy that's caused by oriented stress fields and aligned fractures in the earth and in shale reservoirs. You see a picture of the model. You've got background geology in those two panels, and then the 3D display, you've got those bodies at the bottom of the model, which represents sweet spots in the shale. And there is actually complex anisotropy, so variation in the speed at which seismic waves travel in different directions through the earth throughout the model. And the idea was to see if the anisotropy associated with the sweet spots, those geobodies, those isolated bodies at the bottom of the display, represent organic rich zones in the shale layers, which actually generate most of the production in these shale reservoirs, to see if those features could be distinguished from the background. Again, just to highlight the complexity of the data and some of the tricks that you can play with synthetic data. The other complication in the Barrett model is that the near surface, the region just below the Earth's surface, was complicated. That's another complexity that occurs in land seismic exploration because of things like buried topography. So the right panel shows the topography buried beneath the surface, which is causing rapid variations in the seismic velocity that obscures everything that lies beneath the first couple hundred meters. On the left, what you see is a neat trick that you can play with synthetic data. So what you can do is simulate just the near surface response and its complexity. That's shown in the panel in the top left here. Then you can simulate separately the basin and the reservoir response. I won't go into the technical details of how you do that the right way, but it's easy enough to do when you have the full model with modern numerical modeling techniques. And then once you have those two responses, you can combine them at different signal-to-noise levels to get different challenges for seismic data processing. So in the bottom left, you see the total response, the overburden, the near surface, and the reservoir response at low signal-to-noise, so you can actually pick out those curved events that are coming at sort of shallow curvature across the model. Those are actually reflections from the reservoir layers. So that's at low signal-to-noise level, but you can also boost the signal-to-noise, so increase the relative amplitude of the overburden, the near-surface response with respect to the basin and reservoir response, and create a strong challenge for seismic imaging. And this has already been studied by several of the companies that were participants in the Barrett in SEAM Phase 2. Just to reference again what Joseph mentioned, you know, even though we know the answer for the Barrett model, in fact, precisely because we know the answer, the topic of whether standard seismic processing can unravel all of the effects in the Barrett model has been a trending topic in the exploration seismic literature for almost a year now. It started last October with a talk at the annual SCG meeting, and then was followed up by this paper that's on the screen that was published in February in the SCG's trade journal, The Leading Edge. As you can see from the title, the authors are questioning the ability of standard processing to do the task. A skeptic's view of what's called WVV AZ, and AVAZ, I won't go through the acronyms, but basically different ways of extracting the azimuthal, the variation of of seismic wave propagation with direction horizontally through the model in this Barrett model. There has since been a reply to the authors pointing out some of the weaknesses in their methodology, and now I'm actually working on a paper with the team that did the original seismic modeling, and we hope that that paper will clarify some of the issues that are going on here. So the bottom line actually is that the authors are pretty much right here. The shale sweet spots, the anisotropy that's buried in the shale layer in those isolated regions, they are likely to remain invisible if you just apply standard seismic processing that's intended to highlight anisotropy to this model. It's obscured by the variations in the near surface, and you have to do very careful processing, and you have to look very carefully to see the anisotropy. It's there in the data, but it's very much hidden. Just another thing, that these models are complex enough to be repurposed for different applications. Won't spend a lot of time on this slide, but I'll refer you to the paper. This is a group of scientists from ExxonMobil that use the Barrett model to study ground motions that might be expected at the surface when earthquakes are induced by injecting water at depth. Now, that induced seismicity is usually not caused by injecting water for fracking itself, but for disposing of the water that flows back to the surface after fracking, and that has happened already in a number of states, and also in a very famous example in Basel, Switzerland, associated with drilling of a geothermal well. Joseph talked about the foothills model. Again, just to emphasize that if this is synthetic data from the foothills model, before this model was computed, most of the examples in the literature had dealt with flat surfaces. We all know that the Earth is not flat at the surface. There's a lot of topography, particularly in mountainous regions. And these three panels are just showing the complications that topography and the alluvial fill that's actually present in the valleys gives to seismic data. A geophysicist looking at this data would think not only that it's real data, but it's pretty bad real data. It's very messy. But it is repeatable. That is the exact data. And if you actually do the processing correctly, you can back out those effects using the synthetic data from this foothills model. Arid model, again, has more of complications due to near surface. This is typically what occurs in karsted regions, desert regions where you get dissolved cavities that are filled with air or sand. Again, these are synthetic data that you see on the left and right, and just illustrating the complexity. There is no information that's visible in these shot gathers that's coming from the reservoir at depth. All of what you're seeing is scattering from the near surface. But again, those events are present there. If you process the data correctly, you can extract them, but it has to be done carefully. Another feature, Joseph really didn't spend much time on this, that there's non-seismic data. Non-seismic is the term that seismologists use for all the other data that geophysicists collect: gravity data, magnetic data, electromagnetic data. They just call it non-seismic data. And this is an example from the ARID model showing if you do a simple gravity survey over the model, which is what's shown on the left here, measuring the gravity gradient, the vertical gradient of the vertical component of gravity. You actually see quite clearly where the karsts are, those circular features in the gravity data. You see large ones, you see small ones, and that could be a tremendous help when you actually go to process the seismic data. There's also EM data. I will skip over that. Joseph talked a lot about seam time-lapse, so I won't go in detail through that. Here was what Joseph referring to about modeling the gas coming out of solution in the reservoir. That was done in the modeling of the time-lapse reservoir, and that had very significant effects on the seismic data over the course of the lifetime that was simulated for this reservoir. Here's another trick that you can play with synthetic data for these models. This is showing that you can actually decouple the time-lapse response, the difference between the initial response of in the seismic data of the model and the response after, in this case, almost 3 years of production. There are two effects going on in the full response. They're purely geometric effects as the rocks move up and down. The reservoir contracts as the pressure is released and the fluids flow out. And there are also effects coming from physical property changes as the fluids flow around and oil, water, and gas moves to new locations. You can't see that in real data. I mean, you see the combined effects, but here in this synthetic example, you can actually separate those effects and see how they affect the final data individually. Okay, I won't go through the rest of that, which is where those data sets are available. Let's talk briefly about the ongoing SEAM projects. I'll try to do this in no more than 10 minutes, so we have at least 15 minutes for questions and for Joseph to finish up. Again, here's the list of projects and models. Talk about the 2 projects in progress. SEAM Life of Field started at the end of SEAM Time-Lapse in 2016. Will finish in 2020. It is looking at 2 separate models, a deep water clastic model with salt that's like the SEAM 1 model, but it is built differently and has different features. And we're also looking at the first carbonate model. That's a carbonate ramp model that's designed to contain the features that are present in giant Middle Eastern reservoirs. So that's SEAM Life of Field. It's wrapping up now, and then SEAM AI at the bottom. That started in September of last year. It's still getting its feet about what it exactly wants to do, but 2 goals that have already been agreed upon are it will do collaborative research on applications of artificial intelligence and machine learning, and not just geophysics, but beyond geophysics, geophysical remote sensing in general for groundwater monitoring, environmental monitoring, but then also other aspects of data collection and areas that can be automated in oil and gas exploration and production. And then secondly, and also as important, it's going to look at enabling the design of collaborative workspaces and platforms for geophysical remote sensing. I can't talk in detail about the technical aspects of these projects because they are still confidential to the members, but just to give you a little idea of the flavor of what's going on. So SEAM Life of Field, simulating production and monitoring of 2 large earth models with hydrocarbon reservoirs. The salt model shown in this cross-section display. The green area is the salt. You'll see there are 2 reservoirs, one at the flank of the salt, one underneath the salt canopy. And then on the right is the SEAM carbonate model, which is this carbonate ramp It's kind of this flat section of the structure that then dips down. That's the reef area of the carbonate platform, and then it dips down to down the continental slope to the base of the ocean, wherever these are present. And they are present all over the world. Gulf of Mexico. I'm sorry, they're present in. I have a slide that shows that Florida, Australia, Middle East, etc. This is an ancient carbonate platform, of course, that's been buried and turned into a hydrocarbon reservoir by natural processes. Here is a cross-section through the clastic model, again showing the salt in this complicated pattern canopy at the surface. There's a reservoir at the flank of the salt, and then there's a reservoir underneath the salt that's caused by layers being pushed up by what is termed the mother salt layer. That's the original salt layer at depth that was pushed up by geologic processes, initially in narrow channels, like the one I'm highlighting here with my cursor, and then it spreads out at the top to form these salt domes and salt canopies. And the aim here is to study the production of both reservoirs to see if there are interfering effects as you produce one reservoir, and that causes changes in the stress field, which are communicated by the salt layer up to the surface. So initially, we're just producing the bottom reservoir, but the stresses associated with fluid flow are propagating to the surface and affecting the reservoir that is shallow. Here again are two just displays of the model. The salt flank reservoir is off here to the side of the main salt dome, and then the salt cord anticline reservoir is beneath the salt canopy. Another display. And then here is the first example of changes in the stress state of the reservoir from the production. You can see these are the actual wells that are being simulated in production. It's simulating a deep offshore platform with many different legs, so vertical wells, then deviating to these deviated wells that actually drain different sections of the reservoir. And what you're looking at this slide is the change in reservoir pressure. You can see it's being drawn down by about 15 megapascals after 2 years of fluid flow in the model, and that is affecting not just the changes in rock properties that are caused by fluid substitution, but also by changes in the stress state of the rocks. Here is the display of the life of field carbonate model, carbonate ramp structure that's coming off the rim of a carbonate platform. Again, modern example, Saudi Arabia, Bahamas, West Florida, Australia, among other places. And the idea here is to simulate the complex production strategies that are necessary to fully complete and produce these carbonate reservoirs, which have highly complicated permeability and porosity structure. This is just two displays of the reservoir itself. You can see on the left, here's the main reservoir containing the oil. There's the gas-oil contact in red at the top of the reservoir and the oil-water contact at the bottom. And on the right shows the complex internal plumbing of the reservoir. There are several faults that break up the reservoir into different fault blocks where we're testing different production strategies. And the lines that you see in different colors are a series of 57 producer and 43 injector wells that are draining the reservoir. Just one example of production. I'll skip this one. This is just showing primary production from a horizontal well. The area in red is oil, and it's being depleted over time by primary depletion, then 5 and 10 years of water flooding. Here's the most interesting part, which is this reservoir being produced by a technique called alternating water and gas injection, or WAG for water alternating gas. And the idea is you inject water, then inject gas, usually CO2, into these reservoirs, and the gas mixed with the water that's already injected under pressure will travel further and drain more of the pore space in these complex reservoirs. And then last but not least, we'll also simulate over-injection, where you build up at the last stage of production pressures in the reservoir to continue to sweep the oil that actually can grow large enough to reactivate existing faults. And that has been one of the problems with water injection and overpressuring of several of the large Middle Eastern reservoirs. They don't talk about it much, but it is something that happens. You get earthquakes induced by this overpressure from water injection. Okay, really quickly on CMAI, because it really has just gotten started. It began in September of 2019, runs for 3 years. We'll look at controlled research experiments and applications of AI and machine learning in exploration, development, and production of hydrocarbon reservoirs. Initial applications will be in geophysics, seismic, non-seismic data, but we also hope to extend the methodology to drilling and production control. Project will look at the design of collaborative technical workspaces for oil and gas industry, drawing on sea models and data. We will start with this data set that is out in the public domain. It's real data, field data that was collected off the northwest coast of New Zealand in 2004. It's called the Parahaka data set. It's in the public domain, and the benchmark for our first challenge that we'll publish for an automated ML interpretation, the benchmark against which the automated interpretations will be measured, is an expert geologic interpretation that was carried out by Chevron over 2 years, not continuously, but many hundreds of man-hours were put into that, and Chevron is donating that interpretation to SEAM and SEG to further the state-of-the-art in this field. The interesting parts in this model are a series of channels that you can see. These are canyons that are created when sediments flow down the continental slope and carve out existing sediments on the slope. That's pretty much it. I want to leave some time for Joseph to wrap up with future projects. I have a slide here on how sea models are built. Bottom line is that when we started in 2007, they were mainly built by hand. It was very time consuming. Some of the steps were automated, and now they're almost fully automated. So there are a series of developments in geologic process modeling that have made the construction of these models much easier. It's not yet fully automated, but it is getting close. The only thing that you really need for manual intervention is to calibrate the different processes that are run on the computer and make sure the final result makes sense. Joseph, that's all I have. I can pass it back to you.
Thank you very much. Okay, Mike, have you released?
I have released, but I don't see the. I don't see it yet.
I
have stopped sharing, but.
Okay, let me see. Yep, I think I have it now.
Yeah.
You see? Yep.
Yep.
Okay, so quickly, I want to talk about what we think about the future, what it might be. Here are a couple of projects we talked about recently. I only want to talk about CO2 sequestration. And so if you look at the words here, the picture, of course, is from LBNL in all the reports there. So very nice picture. So what we want to do is, okay, how can we use geophysics to monitor CO2 in the ground, that it's safe, that it doesn't migrate to faults when it stays in the ground, how much can we put in, and so on. And so if you look at the words, it's exactly the same like what I wrote about the life of field. So we have a simulation to calibrate the sensitivity to time-lapse survey responses, the changes in introduced CO2. So the idea is simple. If we know, we can see what happens to the subsurface if we put stuff, if we remove stuff. So we should be able to see what's going on if we put stuff in. So very simple, just turn it around. So the Life of Field project, we have learned quite a bit about workflows and algorithms and so on to do exactly that. But now CO2 is, of course, different. It is different as who would be the beneficiary B, how do we get industry involved? The economics, of course, are completely different, or even absent, you might say. And would it be useful? Do people, experts, think it would be a useful tool to have also in this field, like Mike just talked about in the other fields, where the answer is a clear yes. And so is it useful for CO2 sequestration? So to answer some of those questions, we had several meetings with experts from different organizations, academia, government labs, and industry, and experts from a variety of disciplines. And also, many of those people who participated in those meetings were also working on the SCG CO2 Research Committee. And the answer regarding usability, or is it useful, was the experts say, yes, it would be a useful thing to have. So here is what we came up so far with the proposed program. A big component in this one would be passive monitoring, meaning listen for cracks developing as we increase the pressure to put the CO2 in, and so microseismic monitoring. However, the state of microseismic, there's a kind of an industry around it, but if you talk to all companies and say, okay, how is that going? They say, well, not so much. We give the same data to different companies, and they're completely different answers. So what needs to be done to make it useful for CO2 monitoring is we need to canvass what is the state of the art right now, and build a model to do this and give it to contractors, to companies, and let them work on it and see how much do the answers differ. And then we can do that because, again, we know the answer. And then use those models, hopefully, to improve on the algorithms to get a better responses to event location and event characterization from microseismic. So that would be one, and that could be used for CO2. The other component would be active seismic monitoring, like in life of field, again, using time-lapse seismic. One additional complication is, of course, the rock physics. The rock physics is more complicated than in a usual classic reservoir and even a carbonate reservoir, because CO2 is a strong solvent, and it causes the dissolution and precipitation of sorts. So the rock itself, the rock matrix itself is changed. And right now, there doesn't exist any good rock physics to deal with it. Still, there seems to be a consensus that it still would be useful to do something like this. Like, all models are false, we know that, and so this one might be more false, but hopefully it will be useful. And then we can learn and inch our way towards a better understanding of the rock physics, and even might even have a rock physics component in that program. Again, we would, of course, use surface and downhole seismic. Then the full suite of gravimetric, electric measurements, like before, and have, again, we would have coupled multi-flow, multi-phase flow, and geomechanics simulation, like in the life of field and like in the pressure prediction project. And additional component, we also propose to put in a model, the induced seismicity. So the models that would need to for this work would be a small test model for microseismic testing capabilities, and then the reservoir size model like a field for time-lapse. So there could be a depleted gas field reservoir, saline aquifer, which are the two which are most talked about right now for CO2 sequestration. It's not clear land or offshore. The participants really would need to decide what would be the most useful right now. And then there's the question, do we use an existing CO2 testing site? So there are pilot projects in the field right now which for CO2 sequestration, And you might want to think about using one of those fields and make a synthetic from those fields, and we can not only have synthetic data but compare it to the real data. So that might be an interesting way of doing things. But, the final decision, of course, is not done yet. Who would be the participants? As I said before, there is limited commercial incentive for oil and gas companies, with the exception maybe of enhanced oil recovery. So we believe there is clearly a role for public-private partnership. Universities and government labs have done most of the work, at least a large amount of the work which is done in CO2 sequestration so far. Of course, we need to get oil gas company and industry participation to transmit knowledge. So because eventually, if it's done on a big scale, like we hope it will happen, then it will presumably be contractors who do the seismic monitoring and oil companies who have the people and the knowledge to deal with oil and gas fields and pump stuff in. So the participants would be industry, hopefully DOE labs and academia. So far, we only had industry participation in terms of with the project fees we have so far, the 60K, for example. That wouldn't work for academia, and that wouldn't work for government labs either. So the new thinking is required. Maybe they could participate as a contractor. So that's, but I think we should involve definitely labs and academia who have the benefit of the expertise there. That's what I had. Thank you very much. Are there any questions? Do we have time for questions?
Yeah, it looks like we have about at least 5 minutes for questions.
Yeah, this is David Allen.
Who wants to ask questions can unmute themselves.
Yeah, everyone's muted right now.
This is David Allen. Yeah, I have I guess 3 questions, 2 of technical and 1 that's more how do we collaborate type of question. The 2 technical questions are, and if you can't answer this because it needs to be for project, I understand that. Number 1, in your unconventionals model, you said there was the sweet spots. I'm just wondering what makes them sweet in the geophysical model. Is it just enhanced brittleness, or is it something else? The second question then is, there is lots of discussion about geologic noise that are included. I'm wondering, what other sources of noise do you add to the data? For instance, is there, for land data, do you add some sort of atmospheric noise that might be wind related or something like that?
Yeah.
And instrument noise, what type of instrument noise?
Okay, let me answer those first and you get to the third question, David. Both are great questions, as would be expected coming from you, David. First one, the sweet spots are variations, as you mentioned, in brittleness and organic content, which are represented. It's intended to be a shale gas reservoir, so high gas, low gas. And basically, it has to be translated into a seismic property. So that affects the density and VPVS. So those regions have varying density VPVS from the rest of the shale, and that's what makes them sweet spots geophysically. That's what you should try. You know, the processors are trying to extract, in addition to the orientation of the fractures for the anisotropy. The second one, we don't add any extraneous noise. We leave that up to the members. But I can tell you, for example, what BP did is they took the base data, you know, the clean data, and they actually recorded seismic noise with geophones, you know, coming from equipment running, trunks going back and forth, wind. They scaled that and added it to the data, so they got what even looked more like real data. And you can play around with any of that with these models. The nice thing is that you have a base set of data that is absolutely clean, and you can add noise with whatever statistics you like. So that's how the members are doing that. We haven't done any of that because we leave it up to the members and now the public, since these data sets are out there.
Okay, so they're basically, they have their own almost proprietary description of what they think the noise looks like based on measurements and analysis they've done in the past.
Yeah, that's right. That's what BP and I think others have done.
Okay, cool. Then the last question is more it was covered in Joseph's last slide about the CO2 and possible collaboration CO2 model, but I'm just wondering, data sets like if there's a project that comes up at a DOE lab where it would be really great to have access to one of those data sets, is there a mechanism in place for DOE or for a lab to get access to one of the data sets? Or do we have to somehow run it into our budget to, pay the fee?
Yeah, we had this discussion. There are some data sets where you have access right away because REPSI paid for it. So those data you could have right away. Otherwise, we discussed not too long ago on the board of directors last year when I was still on it. Okay, what do we do with government labs? Do we need to make a distinction between commercial and non-commercial? And Shelley, exactly, how did we come up with that discussion? Did we get government labs in a non-commercial category? Right? Because the prices are different. The non-commercial that they pay a fraction of what the commercial entities pay. So that's really what it's about. And then we have for many projects we have now small subsets, and they're even cheaper. So a prime focus has been foreseen. We need to get enough income so we can continue to work. To pay the overhead and so on, but we want the models to be used. We are not for profit, obviously. We want the models to be used. And so if you have a specific data set you want, you can look at the website and look what you would pay as a non-commercial. And then we... and if that doesn't work, then contact the board, contact Shelley. You can find those on the website and see what could be done. We need to the constraints our team has is we need to be equitable. We need to treat everybody the same. Let's see, that's about it. But we want the data to be used, so we would do whatever is possible to help out. So, okay. Yep.
Other questions, comments? Just to follow up on what Joseph said, the data sets that were sponsored by DOE through REPSI and NETL are the anisotropic version of the Phase 1 model. Phase 2 model was fully funded by the members, but then the pore pressure prediction and time-lapse model, all of those had significant funding, in some cases all of the funding from REPSI, so those data are available to DOE labs. Last questions, comments? I think we're coming up on the time, if we're not even over the time now.
Well, if not, I would thank you, everybody, for participating and listening. Appreciate it.
And Terry, Joseph and I are happy to share these presentations. I don't know if you make them available to the members, but there's nothing in these that are confidential, of course, to SEAM at this point.
Okay. Will send that to me. I would appreciate it. And thank you very much for joining us today.
All right.
Thank you.
Thank you.